Thanks again for the opportunity, and hello to everyone. So the stochastic gravitational wave background is one of the key observables of future gravitational wave detectors, since it provides access to the stages of the early universe inaccessible by any other means. More generally, the stochastic gravitational background is defined as a random gravitational signal produced by a large number of weak, independent, and unresolved sources. There are two possible generation mechanisms. The astrophysical one, which is originates from the superposition of the large number of unresolved astrophysical sources, like in spiraling supermassive black hole binaries, merging black hole binaries, rotating neutron stars. And there is a cosmological one, which originates from the early universe mechanisms, like inflation, where we can have the irreducible background from the quantum tensor fluctuations of the metric during inflation, as well as source gravitational waves from the excited gauge fields as in axial inflation. Gravitational waves can also be produced by the second order scalar fluctuations, which are related to the formation of primordial black holes, as well as strong first order phase transitions and cosmic strings. Given such a large variety of sources, we need a way to distinguish among different backgrounds. One of the possible ways is of a frequency profile, since most of the cosmological backgrounds will peak at some characteristic scale, which will differ from the scaling in the case of astrophysical one from the binaries in the inspiring stage. However, given that future interferometers will have a much better angular resolution, anisotropies in the gravitational wave energy density could provide a new tool to distinguish among various sources. Like for the CMB, the energy density will consist of the leading isotropic contribution plus small fluctuations, which can be either induced at the moment of production, and so they will be greatly model dependent, as well as during the propagation through the universe. Here is the plot of the sensitivity of LISA to various multiples of the stochastic gravitational background. As can be seen, when the isotropic background is detected, the first few multiples will not be so far away. To obtain the linear anisotropy of the stochastic gravitational background, we can solve the Boltzmann equation for gravitons at first order. However, there is an alternative way for the anisotropy at the large scales, which we can obtain non-perturbatively. In geometrical optic limit, gravitons can be considered as massless, collisionless particles propagating along null geodesics. We can define a phase space distribution function for gravitons, which will be a function of conformal time, position, and co-moving momentum. The evolution of distribution function is described by the Boltzmann equation, which in the absence of collisions, we will have the following form. And so the graviton distribution function will be constant along the trajectories of the system. And we can connect the distribution function today to the one which at the emission. Further, the perturbation in the distribution function it can be related to the energy density perturbation of gravitons with the following equation. The average energy density of gravitational waves is typically parameterized by the frequency power law with such spectral tilt. Then the isotropic component of the distribution function can be also written as the power law, and expanding up to the first order in perturbations. We get such equation where the function gamma is the first order anisotropy at first order. We can generalize this equation by considering that this is just the first order approximation of the total graviton distribution function, which can be parameterized by the power law with the exponential prefactor, which denotes the anisotropic contribution. Here, the function gamma contains all the directional dependence at any order. Then substituting this into the previous equation, we can obtain the non-perturbative expression for the energy density perturbation of gravitons, which will include the initial condition induced the initial anisotropy generated at the moment of production, as well as the anisotropies due to the propagation through the universe. That will be the Sachs-Wolfe effect and integrated Sachs-Wolfe effect contained in the ratio of comoving momenta at emission and arrival points. Now we can obtain the initial conditions, which in the case of the gravitational wave background from the quantum fluctuations of the metric during inflation can be obtained in the non-perturbative way. We consider a perturbed Friedmann-Robertson-Walker metric in the Poisson gauge, going beyond linear order. Scalar, vector, and tensor modes will be coupled. And so we have to consider this. However, given that in the we can neglect vector modes, since in standard single field models of inflation, as well as in other early universe mechanisms that generate gravitational waves, linear vector modes are not produced. While at higher orders, they will be functions of spatial gradients of scalar modes that we can neglect, as I will explain later. In the short wave approximation, the tensor modes can be split into the small-scale ripples, which we identify as gravitational waves, and the large-scale tensor modes. Since the wavelength of gravitational waves is much smaller than the one over which the background varies, this justifies such a splitting. And we will also neglect the large-scale tensor modes, since already at linear order, the primordial tensor power spectrum is suppressed by the tensor to scalar ratio with respect to the scalar one. We can also split scalar perturbations into the subhorizon and superhorizon modes. Assuming that the gravitational waves are well inside the horizon when we compute initial conditions, we can neglect the large-scale, the spatial gradients of large-scale scalar modes, since their wavelength is outside of the horizon at the moment, and so they can be considered only as functions of the time. Then we can reabsorb this large-scale perturbations of phi large and psi large into the definition of the metric by redefining the scale factor and the conformal time. We also have to redefine the small-scale tensor modes, to avoid mixing scalar and tensor perturbations in the definition of gravitational waves. Then this new redefined metric will describe a homogeneous anisotropic universe on large scales, plus the small scale tensor modes. Then we can compute the energy density of gravitational waves. Writing the energy momentum tensor in terms of covariant derivatives of gravitational waves, which are defined in these prescriptions in the following way. And then writing the standard average energy density, which is quadratic in small scale modes. In this new redefined metric, it will correspond to the total energy density, since the large-scale scalar perturbations have been reabsorbed into the metric. And so we have the total energy density. Here is the average energy density plus the this exponential prefactor, which contains large-scale scalar perturbations. If we to connect it to the standard perturbative approach, we can expand it to the first order, and we obtain the result that we have in our previous work for the inflationary initial conditions, which we can then connect this energy density perturbation to the perturbation of the initial perturbation of the Gravitational distribution function. The inhomogeneity is due to the propagation of gravitons are contained in the ratio of comoving momenta at emission and observation. We can obtain this ratio by solving the zero component of the geodesic equation for gravitons. Then we obtain the following result, where the first term is the Sachs-Wolfe effect, and the last one is the integrated Sachs-Wolfe effect. The second term will contribute only to the monopole signals, which can be disregarded. Then substituting the ratio of comoving momenta and initial perturbation of Gravitational distribution function, we can obtain the non-perturbative generalization of the cosmological gravitational background anisotropy on large scales. And due to the exponentiation of the gravitational potentials, it is fully nonlinear. Here is a plot that we obtained in our previous work for the angular power spectrum. Here on the top is power spectrum in the case of this inflationary initial conditions, and where we get the enhancement of the angular power spectrum in comparison to the adiabatic initial conditions. This nonlinear anisotropies can have an effect on the higher order correlation functions. We can express the non-perturbative Sachs-Wolfe effect and the initial condition term in terms of the comoving curvature perturbation. And so to relate the anisotropy today to the initial conditions set at the end of inflation. From the continuity equation, we can derive such a quantity f, which will be conserved at any order in perturbation theory, and the perturbation of f will represent a nonlinear generalization of the comoving curvature perturbation on superhorizon scales. Then computing this nonlinear theta using the equation of motion for the radiation domination, since most of the future gravitational wave detectors will be able to probe the frequency range, which corresponds to the gravitational waves re-entering during the radiation domination era. We will also need the total energy density in this new metric, which we can infer from the 0, component of the Einstein equations. Then the scalar perturbations are related by the transverse traceless part of the Einstein equation in the Poisson gauge. And at higher orders, this equation will contain non-local terms that we can take into account by introducing a suitable kernel. Then we can express the perturbation of Gravitational distribution function in terms of the comoving curvature and as well as this kernel. And we noticed an interesting property of the scale-invariant power spectrum. In this case, kernel vanishes, and the perturbation of the distribution function will be only dependent on the comoving curvature perturbation. Then we can define the gravitational wave energy density perturbation in such a way where A is a normalization coefficient, so that if we take the ensemble average, the density perturbation is 0. In the standard single field models of inflation, the primordial non-Gaussianity is negligible, and the only contribution to non-Gaussianity comes from the nonlinear evolution of gravitational potentials. In this case, the quantity zeta will be a Gaussian quantity, and so the energy density perturbation will be lognormally distributed, which can lead to such effects as intermittency that will consist in the emergence of isolated high energy density spots, which will be separated by large underdense areas. And this property can distinguish cosmological background from the astrophysical one. Then to compute the endpoint correlation function, we can use the path integral approach, introducing the generating function of the correlation function in the following way. And then by taking function derivative of zeta, we get the endpoint correlation function. And then defining a new functional as a logarithm allows us to obtain the connected correlation function. Then using the property of endpoint correlation function for the exponent of the Gaussian random field, since we assume zeta to be Gaussian, we can easily obtain the two-point connected correlation function for the gravitational wave energy density perturbation, as well as the exact three-point connected correlation function, which can be written as a function of the 2 point ones. And due to this particular property of the exponents of Gaussian fields, this result will be exact and hold at any order in perturbation theory. So to conclude, since general relativity is fundamentally nonlinear and higher order corrections leave their imprint on cosmological perturbations, assuming that the distribution function of gravitons can be parameterized by a general power law, we can connect the initial anisotropy to the one we observed today, going beyond perturbation theory. As well as these nonlinear anisotropies can have an effect on higher order correlation functions and can be the source of non-Gaussianity. Besides the primordial contribution generated during or right after inflation, non-Gaussianity can be caused by the nonlinear evolution of gravitational potentials. And using this expression for the anisotropy of cosmological background in terms of the comoving curvature perturbations, we computed non-perturbatively the three-point correlation function. And an important result of this work is that in the case of the background generated by the quantum tensor fluctuations during inflation, with a scale-invariant power spectrum and negligible primordial non-Gaussianity, the kernel which contains further non-Gaussian contribution will disappear. And then the gravitational wave energy density perturbation will be lognormally distributed. This will also this allows to compute the exact 3-point correlation function, as well as it makes the Sachs-Wolfe effect of the cosmological background completely insensitive to the presence of gravitational sleep, which can arise either from neutrinos or by modifications of gravity. And even this will be the case even beyond the squeeze limit, unlike in the case of adiabatic initial conditions, and unlike for the CMB, where it is possible to have the vanishing kernel only in the case of squeeze limit. However, the effects from the anisotropic stress will remain in the integrated Sachs-Wolfe term. Thank you for your attention.